Okay, I'm chasing the rabbit tonight pretty good. Let's get over here, see if I can do this up a bit. Actually, I'm working on this fundamental analysis, or functional analysis problem still, because it's always that damn base matrix. It's that first step that's a killer, right? You got to get it just right. And they'll give you shit like this. Just a reminding context. Go to functional analysis on the internet. It's a college class, and a guy's going to get you a bunch of shit that when you write it down is going to look like this. Kind of looks like this on the chalkboard, but then he erases some shit and he does some stuff. And that's a byproduct of something that's really super important to understand here, but then he just hits you with everything under the sun, alpha, beta. It's basically alpha radiation, beta radiation, gamma radiation, X being eat it, sit on it, or throw it out the window. So you wind up with this really simple base matrix out of it. You're just really cicada your way through there. You don't even understand. There's so many steps that this stuff has to byproduct here. But I'm going to describe generally what that looks like in this build. I'm actually going to turn this first page into a ball in air, a ball in water, and try to work my way to a beaker with it, because this is a lot about vector fields, scalar fields, vector positions, figuring out the mass by acceleration and velocity in relative atmosphere. And we got to do that by something like describing it first very simple in something like a Big Bang type application that starts to rip away for some supercomputing that has to be done in this. Because like I said, when I describe this in a general set, I break it down in ones and zeros and x's and y's, because generally there's an extra system. We know with computers, being the physical proof of this, that there's some kind of dimensional x of superpositions of needing to distend or compress this in some way by whatever geometry you want to use as your right hand rule to determine time. And so the first things first is that this is an idea of what I put up here first in general respect for it, but the field theory, Einstein's field theory equation, the Laplacian, the metrics here, 8 pi g t metrics, grad school, and then any other time that's quantifiable by that. You don't really understand what that means, because to you it's not a general thing. What you come to find out here is that is the first initial step while determining what this ball in air and ball in water conceptual model is about. It's not about having to use this ball in air water later. It's when I deal with something very simple later, did I use this field theory to determine what that function is? Am I using this process of going through it, ball in air, ball in water, 42? And later on, as I build this through, you'll see in my next step to a x on y function in this inverted. It hasn't figured out gravity yet, doesn't know it's a ball in air, doesn't know it's a ball in space, doesn't know it's a ball not moving in space in terms of relative other objects and orbitals that hold it into what would be relatively something different later. And that is to say, an in-field report. The mathematical standards is break it down, do this kind of system, failure proof you into the ground until you understand, graph it later. But an in-field report is specifics about which ball, the special relativity behind this, and of course into a second base of this, the base field reporting Newtonian limit. And that's going to be an omega inside here. That's to say, whatever fundamental action after report, they are the general field theory by the terms of mathematics that you're using, but I'm breaking off the larger bits to operate the process like it's a Laplacian method, like it's Bell's equivalent or field theory satisfactory in terms of applying the approximations of what is, again, when you look at that, essentially a black hole of a field theory equation. We're going to learn to backtrack and reverse engineer. But before we get there, we're going to have to talk about this y function down here that is in the x position, where this concept starts to break down and get a little loose before we get into this two-dimensional, three-dimensional timeline, written word, code ciphering kind of stuff, before we get into, again, the metrics, the scalar fields of what that is, before I start to break down how exactly I want to break down the air and ball. It's a matrix. I got to figure out kind of how I want to play it, but I also want to put another metrics inside here before I start to graph something later. Just as a quick little insight of where I'm going on this first page. And as you actually do this, it talks about the inertia of that concept in the second position. Now, how do you know that's second position? A whole hell of a lot going on here. Well, generally the way the mechanics are going to work, it's not going to matter if you go to the A plus B equals C or all initial letters, numbers, letters, or any symbol-based systems of field theory, in-field reports. They are A's, they are 1s, they're X's and Y's, and superposition later on. We'll get into some heavy-duty stuff with this, but I want to do it with a very simple matrix within that principle that defines what this characteristic is, because we know it's the Big Bang, we know it's computers based on that kind of notation of, at least as a physical field theory, moving towards a direction in a right-hand rule will be important later. But this is, say, inertia. An object in motion is going to stay in motion unless acted upon by another force that changes that idea, and this is to say the second law of motion. Well, we'll build into that, but it's actually all that code in field theory, letters, numbers, symbols that apply the general value when you want to determine what you're adding A plus B to, or 0 plus 1 equals 1 on a right-hand rule. I'm not going to get into apples and oranges and it equals a fractal without the algebra A plus B equals C, Y plus Z equals Y, because F1 plus F2 equals minus F1, and Z plus Z equals Z. And it's an end function. F1 plus F2 equals minus F1 plus F2 minus F1 plus F2. That gives you still the same result, ball in air, ball in water, but it changes certain properties. It gives me a better insight about the opposites of this function when I say Fn equals ma, the force in a net equals the motion of acceleration. So as the ball moves, so does the frame of reference in general, and we're going to talk about that, like how it's easier to square the area over a lake, or what is the area of this lake, or if you go 100 feet up, what would be the relative volume of air that could be in there in approximations. Now, it's easier just to square that up, right? It's easier just to limit those systems in a generalized way, so I know the approximations of how much mustard gas you need in there, or the elephant drop, or whatever you guys do. You know, and that is to say, that is the reverse engineering. What we know is true about that is the ball is going to fall towards gravity, and what you're going to need is acceleration on Earth first. But this X is relative to Y, right? Because they're the same answer, different on Mars, but it plays the same. Once you have terminal velocity at that point of any ball, then you can determine what all balls rock, baseball or otherwise, until air resistance or something else comes up and differentiates that. When you say for every action, then I put uncertainty inside of here, because we're still dealing with the multi-matrix. We're still dealing with, now I have to figure out what G is. What I know of any ball of that size, it follows those basic rules, but now I'm looking at an object in space coming at me, and that's what gravity is. That's what the IH observation, when you get into the other symbols and letters at 1, A, and some combination of AX, A plus B equals X, A, 1, 0, and all that field theory shit that you're going to get into there is, again, now if you look at that equation, you'd say, well, F equals ma in sort of the situation, and it gives me 9.8 on any ball, bowling ball, feather short of air resistance, is going to follow that rule because gravity follows that function. But what I know is the velocity, not its mass. It's just an object in motion. I didn't have a chance to graph it. That is the in-field report. So what I'm going to have to do is get things like mass times velocity to get acceleration. Like I can generally say it's about that big, and it's generally moving by a velocity indicators of no matter what weight it was or what object it was. If it moves that, we quantify it by an inch, quantify it by a mile. And that's where velocity and acceleration, or velocity and, well, acceleration, and some of the combinations of multiple symbols that can't be triggered in the same way with the ones and zeros need a mathematical form to actually process it out. And obviously there's not a real great matrix to describe what that is mathematically, because there's so many standard models that could describe that first initial base. It's a good way to do it, but is it exactly pure? Is it exactly crystalline? Not in terms of a computer speaking idea, but in terms of ball and water, ball and air, this is where the field theory begins, because it is a singularity, much like the base, that you can jump through to then say, in order to reverse engineer what acceleration was, what object, what first big bang was there, and in a local form use that base. Well, first to use that object to invert the shadow problem to give me base mechanics, but then again to use that base mechanics to invert what that object was, or what portion of it I can then add to other portions as a brick to give me a total approximation. And therefore, where the Chinese satellite's going to land in the Indian Ocean, or megatons for atomic bombs, or whatever value that was going to be, because that would be the velocity that was gained from this, some energy release, which gives me the force overall in a net based on its motion and acceleration, how fast it releases something. And inside of that base, it's going to be all of the approximations of heat, light, and sound, but it's going to be approximated to the averages of those as an energy release, as a general form of all of that. But what really happens when you're there is obviously Hiroshima. That would be the results of that. That's what 15 megatons would look like in a time frame of those elements based on those Penrose and systems. Remember, it's not just things that happen super fast here. As you throw a ball, the actual mechanics of this choice is a ball on the ground, ball X plus X off ground, in terms of ball Y plus Z function. Now, what I wanted to do, this, we're really radically, this is a chemical reaction on different atmospheres, on different topologies with air resistance. The air resistance is fine, but a time dilation at the top of the Himalayas where it actually matters. Throwing the ball isn't just a mechanical option here of why you can't do it, but there's also an additional negative or a positive that would increase because there's less air resistance, less air, oxygen molecules, it's a thinner atmosphere that will go farther. But you're not going to notice that throwing it off something. It's just going to seem like it goes farther than normal. The approximations don't add up on that until it's in some kind of mechanical operation where I needed to do it like that on the top of the Himalayas, or act under the pressures of something like the Marianas Trench. Those are where gravity and velocity of these different subsets still didn't work. Why didn't the Newtonian mechanics work? Because we're just applying the structural model, not applying what type of steel or what type of composition. And again, where those new fine-tuned mechanics would be a little bit more appropriate as a base mechanics to have done, so then it's easy to check and easy to look up and say it's a base of a field theory. Now, again, any one of those field theories is just generally a decent way to topic it, because, we're going to figure out X equals X A, and a whole bunch of math that gets you there. And it's not math, they're actually individual. Okay, so the ball's in air, not inch, up an inch, up one increments, because 1 is 0, 0 is 1. So when I fractal that or system that, it's still based on the vector positions later that you're going to want to graph and give you some kind of indicator of a long time of actually tracking multiple very filled in sensors, servos, types of mathematics, applying those values and forms to companies where it's already done. And you're not overdoing it. You don't want to say, I just want to mass out all the equations, but what you want is a stone mill where you can apply Schrodinger's equation at any point in time, where you can apply the Laplacian, Larry, Dave the flaming graphing calculator method in terms of what vector matrices you'll need. Those are the L brackets of inventory for a mechanic, which is essentially a singularity. Inventory for a mechanic you may think is relative, but let's talk about what type of shop. We're talking about the stone mill, we're talking about Lou, the mechanic down the road. In terms of the G, that is the meters per second that you have to travel to determine what force is net, is going to determine a very different object's acceleration on a timeline if I start them different. Me to know a certain scale of that type and say it on the resume equals FMA, but when you get there to the shop, there was a different appreciation of why the breakdown of these equations, why you start with G in some of the equation bases here, or why to determine what velocity is, or why acceleration prime doesn't do justice to the equation to determine what value that is, when acceleration may have already been notated in the equation, or at least the form in which it was that's now differentiated through some Schrodinger axiom that is greater than the overall wave function of that differential. And so you're going to build a lot of cicada. It's actually going to get into some heavy duty shapes, symbols, and things like that as you actually track out some, especially Nova Strokers or something like that. There's just a bunch of air turbulent derivative. I mean, you go track, it's basically a derivative set where you're just tracking derivative lambda, derivative space, derivative time, derivative, you know, and they kind of over redundant themselves, but what it does is help you narrow down, failure proof. Well, was that the answer you're looking for? Well, students without a real value to look with or go with always need the base metrics, this base physics that says, did you ball and air and water this? Did I figure out where I can make one thing uniform consistently and then change that process in some way in a positive or negative result, depending on the positive negative result that you're looking for that superposition. Again, sometimes it's a notation under FMA. For every action there's an equal opposite reaction, that I need to know the gravity of the situation being IH relative to an object in motion, here in this case a ball in the field of Earth, and why it's practical while dealing with applied physics that way, but at the same time, given what engineering functions that may be there, that you need a real field theory about what that very specific net force value is, what its specific velocities or gravities in this case would be, the breakdown between mass or acceleration and mass being a meters per second thing, being a relative x is what you'll find being zeroed out. Well, what distance is it? Inches, miles, imperial, Roman inches, you know, Roman feet. As long as it's quantifiable under zeros or one, and that experiment is still valid, that somebody else at a different language or a different observer can still quantify what your x is, then that value is appreciated and should be functionable throughout the entirety of the mechanics, even if it's something heavy duty like Laplacian metrics on 8 pi g metric to whatever you want, or Dirac's equation, Schrodinger's, Gauss. You can get into Nova Strokers, and of course the stone mill methodology for any scholar metric or whatever's going to value that. They're all I to me. Any one of them can be environment or sum for what the value is. Sometimes capital form of golden ratio can be sometimes, you know. So you got to be really careful with the method, but as long as you're generally within the object in motion, it's going to be fine. But again, initial relativity movement is super critical to that. Like, I was a stonemason, I was coming into a thing, so you know, the differential is that's the universe where generally the stonemason you're going to stand still or have an initial net momentum that equals zero still. Operating skills, doing things where you're going to pick up real fast, you're going to move with the object not at a negative time, you're not going to see the heat, light, and sound freakies. At the negative square root of -1 is I, being some negative metrics on the positive curves of things that change. Well, he's human, should be able to figure out the job. If I've had other people do that job before, this rock will work, but a y rock to the zeta function, is it still yes or no when you change out the x to the x off ground, where it still works for math, still works fine, but then it's a ball of silly putty. Doesn't do the same effect, but it gave all the same effect answers, and they just act very differently. Now that might be relative, it may not be relative, and at what point on that spectrum does it start to be a different thing with all these equations is well, a track of its own. So catch you on the next one.